This is the 38th lecture in a series on single agent heuristic search. And today we're going to be continuing where we left off in the last few lectures, looking at how we build heuristics in polynomial domains or explicit domains. And we're going to look at particularly today the idea of embeddings. And so we're going to look at where embeddings come from. And we're going to be looking at and what an embedding is. And so we'll go ahead and get started with that. So today, as I said, Euclidean embeddings. The idea here is that we are taking some graph and we're going to embed it into a Euclidean space. And what that means is we're going to take every node in that graph, we're going to assign a coordinate in Euclidean space, and then we're going to use the distances between those coordinates as our heuristic function for doing search in the actual state space. And so if we think about a differential heuristic from the previous lectures, what was going on here? Well, every state was assigned a heuristic. So a heuristic between A and B, depending on the pivot, was equal to the absolute value of the distance from pivot 1 to A. I keep switching the order of these, but we're assuming an undirected graph, so this doesn't matter here, but I'd have to be more careful if we're thinking about a directed graph. Distance from pivot 1 to state B, and we just take the absolute value of that. And so if I look at this, this is giving me, what is this giving me back? Well, from a particular pivot, what's really going on is that, and let's draw this out here, is the pivot is really going to be put right here. This is the pivot, and it's at really the zero coordinate of the state space. And what's going on here is we are putting states onto this one-dimensional graph, this one-dimensional plot. And so I put some state A here, I put some state B here, and what I'm really just saying is that the heuristic is the distance between these states. Now, I have to be a little bit careful here, so let me do this, because in practice what's going on here is that the states themselves are always going to have positive distances from the pivot. So I should really move the pivot over here, and I really start out with my pivot at the very bottom of my state space. Okay, so practically speaking, basically, what do I get here? My heuristic is, well, the distance to B, the distance to A, the difference between that is a heuristic. So what I've done is I've embedded everything in a one-dimensional line. On that one-dimensional line, then I'm just using distances on that one-dimensional line as my heuristic value. So this is the interpretation of differential heuristics, is it's a one-dimensional line. And the question is, well, what if I don't want a 1D embedding? What if I want to do a higher dimensional embedding? Can I do it? And the answer is yes, but we're going to look at two answers to this question, or two ways that we can do this sort of computation. One of them is going to be a machine learning way of looking at the problem. And the other one actually comes from databases. But I'm going to sort of interpret a little bit in the light of some of the things we've learned here, for instance, in terms of our heuristics. So if we think of this as if we want to, for instance, an optimal embedding. So that is, we're going to write a function that we want to optimize. And if we can optimize and actually come up with the optimal value here, then we would actually say, well, this is the best that you can do. But this is, of course, with the caveat, it's only optimal with respect to the function that we're going to optimize. And it's only going to be optimal for a single heuristic. There might be better ways to optimize multiple heuristics. But we could write this down and we say, look, we're going to choose an embedding. And so my embedding is going to be Y, capital Y. And so over all possible embeddings, what I want to do is I want to maximize for all I and j a weight of ij. So we saw this before when we looked at the submodular problem. And then this is a norm, which is just basically the distance in the space we're looking at. So for right now, we just consider it to be Euclidean space of yi minus yj. And we're going to square it. So in this case, we're going to be looking at maximizing the squared. So we're going to try and basically we're looking at the maximizing the squared distance. So what is this saying? We're going to take some particular point y and put it at some, sorry, I. So we can take some location I and we're going to put it at a point y, some location j and put it at a point j. And then what we want to do is we're going to look at the difference between those. So that's the distance. This is the distance in Euclidean space. And then we're going to try and maximize the squared distance over all of our states. This is going to tend to then, of course, maximize the states that are farthest away. Those will get the most weight on them, although we could use some weighting function here to weight how much any particular I and j are worthwhile. Now, this is subject to one constraint here. So we want to say for all I and j that we want inside my state space, which I'll just call it E for right now. I'm thinking about my edges. So if an edge is between, so really ij is like an edge between two nodes I and j, then what I want to say is that the distance in my Euclidean space between yi and yj must be less than or equal to the cost from I to j. And what this is just saying here is this is just consistency. It's saying, look, the distance between two states and the state that I embed them in has to be less than the actual cost between those states. So this says basically take all my states in the state space, embed them into over all possible embeddings in the actual, in a two-dimensional space or n-dimensional space that I'm going to try and embed them in. What I want to do is I want to choose the embedding that's going to maximize the heuristic value I can get back. And then what I want to do is, so I'm maximize the heuristic that I get subject to the constraint that the heuristic must be non-overestimating or that it is admissible. Okay, so hopefully that problem definition, even if you're not familiar with that, is something that you can look at and understand. And if we look at this, I'm not going to go through how this can be done. Again, this is by Rayner et al. So this is Chris Rayner. His PhD thesis, but this is a 2011 paper that talked about how we can basically build an embedding like this. And if you look at this, then what you can do is you can do some reorganization. And if you do that, you can show that the problem is convex. And because we're looking at distances here in the state space, it's not a linear program, but it's a semi-definite program. And so we can solve with a semi-definite program. Which is basically just an extension of linear, something like LPs, but that can run with nonlinear constraints. And what I want to show you, just as an example here, is that we can take a state space, like all four-letter words, and we can take them and we can embed them, and we'll show an animation of this. We can embed them into a three-dimensional state space. So every node here corresponds to a word, a four-letter word in the English language. There are edges between two words. I have to explain what that means, of course. There's edges between two words if we can change one letter in the word. And by changing one letter in the word, we get another valid word. And so when we do that, we can take this graph that initially there's no, this is just a graph of words and they're connected together, but we have no sense of distances between them. Now we can put them into this three-dimensional space as we're visualizing here. And we now can take any two words, and now we can use this Euclidean distance as a measure of the distance between them in terms of edit distance. How many one-letter edits would be required? Not just sort of one-letter changes, but one-letter edits would be required to go through a sequence of actual words in English to get from one word to another word. Okay. So this is just the idea of what can be done here, how we can go into, how we can take a state space like this, we can map it into a three-dimensional space, and then we can use distances in three-dimensional space, Euclidean distances in three-dimensional space as estimates of true distances. Okay, so hopefully that was interesting. It's a fun animation as I said, Chris Rayner put that animation together as part of his PhD thesis. But that's the problem with that, is that it's really expensive. It's basically like computing all pair shortest path, and what we're actually optimizing is the squared distance of the norm. Here's the distance. And so that, again, that could be, maybe we don't want to optimize the square distance here. And so the idea here is we can do another version of this. And as I said, I'm going to describe this to you. So this comes from the database community. And this is work by Sven Koenig and his students. So we can take this from, they call it, it's called FastMap. And I apologize, I don't have the full reference and all the authors in front of me here. But what we're going to do is this idea of FastMap is we're going to think about differential heuristics. We're going to think about what happens in our state space, and we're going to see how we can build actually additive heuristics. So FastMaps are additive heuristics. And my view of them, maybe not everybody's view yet, but maybe my view of this is that a FastMap are basically additive heuristics. They're sort of like an additive differential heuristic. But what happens here is that a differential heuristic, it uses sort of up everything that could be used in the additive space. And so we're going to do a different type of embedding. So the differential heuristic is basically saying, look, I take a pivot here, and I'm going to do I'm doing a uniform cost search or a Dijkstra search to lay out every state here according to the exact distance from this initial pivot. And we're going to do something a little bit different here. So what's going to happen here is we can think about a problem here. So I'm going to draw a very simple problem out, and what I'm going to do here, I'll draw a problem and we'll look at sort of what happens here. So imagine that I take just a very simple state space here. And I'm going to imagine something here that we've got some heuristic. So what we're going to do is I'm going to write in black the edge costs. So let's just say, and just for simplicity, let's just say the edge costs are 2 everywhere. And then what we're going to do is we're going to imagine we have some baseline heuristic. And what we're going to do is we're going to say, for every edge here, what I want to do is say the baseline heuristic, for instance, here is going to be, I'm just going to make it 1 everywhere. We'll make it 0 here just for the fun of it. Then make it 1 here. And the idea is that we've captured, for every one of these edges, okay, I'm thinking about the heuristic across just between these two states. For every one of these edges, I've captured something in this edge. Okay, so I've captured the differential heuristic is well, anyway, I imagine I have the heuristic that is admissible and that is consistent. And now I've captured something here that says, I think that these edges are actually 1 apart in my heuristic, but in practice, they're actually 2 apart. The same thing here. Here, I think they're 0 apart, but they're actually 2 apart. And the same thing here. We don't worry about states that are farther apart because we've actually captured on these individual pieces. Given the consistency of the heuristic, we've actually captured something that's going on the bigger pieces. But the idea here is that this is my original graph. So let me just write it. So this is my original graph. Plus we have the heuristic. And what we can notice here is that there's some things that are not captured in the original graph. And so this is what I would call as a residual, but is what happens if we subtract out from this original graph here the heuristic values that we have on each of these edges. So let's subtract that away and see what's left in the graph. And so the residual graph we have here is going to have an edge of 1 here. It's going to have an edge of 1 here. It's going to have an edge of 0 here. Sorry, I have to be careful. There's an edge of 2 here. And then there's an edge of 1 here. And so the notion is that this heuristic has captured something about this graph, but this portion of the graph isn't captured at all in this existing heuristic. And what that means is that in this residual graph, we can compute another heuristic inside here And if we only compute it by these distances that have not been captured by my original graph and the heuristic on the original graph, then this residual graph can be added. Any heuristic on here can be added to the heuristic on here, and I'll still have an admissible heuristic. And this is exactly actually what's done in our pattern databases. When we think about in our additive pattern databases, what happens? Well, when we do our additive pattern databases from the original state space, what we're doing is we're capturing some of the distances when we have a pattern, but we're only capturing some of the distances, and we leave all the rest of the distances in sort of the original state space. And then we build another abstraction, and that abstraction captures distances that if we think about if we were to think about the original state space, subtracting one additive heuristic from it, there would be a residual that we could then do another abstraction that would basically capture what is in the residual completely. So what we're thinking about is there's basically distances in these different graphs, and if there's distances that haven't been captured here, I can capture them in the residual graph, and I can capture them in a heuristic on the residual graph. And because these distances are not captured at all here, we can add them together. Okay, so hopefully that's clear. And so the idea here is that this is a way of giving us additive heuristics. Now, if we could think for a moment, so here's a question I want to ask. And the question is, what happens if I do a differential heuristic and then I build this residual graph here? Okay, so think about this. You might want to pause the video, but if I do a differential heuristic where I take a pivot, I get the single source shortest path to every state here, and what I'm going to do is I'm going to capture, so I'm capturing this distance for every state here, and so I've got all these distances, and that's going to give me my coordinate. And then what I'm going to do is I'm going to go into my graph, and I'm going to ask like what edges have been captured by the heuristic and which edges haven't been captured, and I build a residual graph and see what I can do on the remaining graph. Okay, so what happens there? And the answer is that when I do that on a differential heuristic, my residual graph will have so if I do a DH residual, what will happen here? It ends up that I will have a residual graph with a 0 heuristic on every single edge. Okay. That would be something like this. And let me actually show exactly what goes on. So let me just erase that. Let's actually look back at this original problem. And so we can look at this problem that's, I need slightly different costs to do this. So what we can think about here is let's draw a slightly different problem. So what we're going to have is we're going to have a start state here, and we have some states here. Let's just put distances here. So I'm going to put A, B, C, D, and we'll just put distance of 1 everywhere. And what we're going to do here is, if I think about a differential heuristic, then what's going to happen here? Well, on my state space, we're going to get S, then we're going to have A, and then we're going to have another point here that is going to be B, C, and D. Okay, and so when we do that, S, A, B, C, D, what happens here? We know from S to A we get a distance of 1, from A to B, A to C, and A to D we get a distance of 1. And so what we've done is we've captured those distances perfectly well, but we haven't captured the distances from B and D. So the residual graph S to A, the heuristic is the residual there is 0 because we've captured that. And then from A to B, we've captured that as a distance 1. So I'm subtracting this out. So just to be clear about this, what are we writing down? We're writing the cost from U to V minus the heuristic of U to V. Okay, and so that's going to be 0. When I go from A to C, the heuristic, the difference in this is going to be 0. And when I go from A to D, the residual I get is 0 there. So what I end up, as I said, is we're going to get a residual everywhere in this graph, although we have not captured at all the distance between B and D, or the distance between B and C. These things have not been captured. Okay. So, and what's happening here basically is when we do this residual, what's happening for every state is we're exactly capturing the shortest path from that state to the start. And we're capturing the shortest path from every state to the start. So when I do this subtraction here, what happens is that on all states sort of going out in my search, I've got shortest distances. So in the residual graph, the shortest distances will actually, there'll always be a zero cost path between any two states. It goes from that state on the shortest path back to start, from the start on the shortest path to the other state. So there'll always, so there may be still a cost inside here, but if there is, there's always going to be, so for instance, you could imagine there'd be an edge here that has cost 1, but I will have captured the actual shortest path, and the remaining graph will always be 0. Okay, so the idea here is that because the differential heuristic is basically stretching these states out as much as it can in the state space, then what's happening here is that we've lost this ability to have any residual in the state space. And so what we can do here, going back to FastMap, is what we're going to do is we're going to do this. Is instead of starting with a pure differential heuristic, we're doing this exactly. Differential heuristic has a single pivot. And for FastMap, we're going to use 2 pivots. Okay, and the idea is we have 2 pivots. We're going to choose sort of a state and another state, typically that might be maximally distant, but they don't have to be maximally distant. And the idea here is, okay, I've got these states that are far away in the state space. And then the question is, where do I line everything else up? So in particular, what can happen is that I can have states that are not on the shortest path. So the shortest path, states on the shortest path basically just have to be aligned along this shortest path here, because that's the only way that we're going to actually embed them, so that distances in the state space give us admissible heuristics. But what we can think about is there might be states in the actual state space that are, we think about, that are not on the shortest path. So there may be some path up here, and then there's some path down here. And these states could really be embedded in quite a few different places in here on this one-dimensional line, and they would still be able to have an admissible heuristic. Okay, so what we're going to do is we're going to say, is basically let's write down this equation and see what happens. So embed point I at location. So it's D. So if we're thinking about between A and B, so we'll call this A, and we'll put this B. So I'm going to say I have the distance from A to I, and I have the distance from A to B, and I'm going to subtract the distance from I to B. And then I'm going to divide this by 2. Okay, so this is the embed point at location, which is this one here. Okay, so let's look for a second. What if I put point A here? Point A, the distance between A to A is 0. Distance from A to B is going to be from A to B. And the distance from I to B is actually going to be also the distance from A to B. So point A is going to go at location. These are going to be the same thing. It's going to go at location 0 here. What about point B? Well, this is going to be the distance from A to B. This is the distance from A to B. And distance from I is B now. From B to B is 0. So I get 2 times the distance from A to B. I divide it by 2, and it says B goes exactly at the distance from A to B. Okay, it doesn't have to be there, but that says where that point lies. So now if we have a point, what we're going to think about is for some other point in the state space. Okay, so here's A and here's B. Just to be clear here, in my actual graph, I don't necessarily have any topology here, but here's A and here's B. and that, there's some other point C here. Okay, so let's look at this, and let's just say that, this is 1, 1, 1, 1. What is going to happen here? Okay, so in my embedding, what am I doing? Well, I'm going to put A here. I'm going to put B here. This should actually be capital A. And then what happens here is we're going to say, look, C here is 2 steps away from A, and it's 3 steps away from B. So what we're going to say, look, the distance from A is 2. The distance from A to B is 3. And the distance from here is also 3. So what's going to happen here is these are the same. These are both 3. This is 2. And so what we're going to say is we're going to place point C here. Okay. So in this state space, we'll embed C right here, because C is basically, if we think about the distance, interpolating the distance between B and C, it's sort of 1/3 away from A, and it's 2/3 away from B. If we did a differential heuristic, what would happen is that we would actually be putting C at this point here, which is sort of maximally distant from A. We wouldn't be thinking about B. Okay, so what happens here because we've done this? So now we can think about, so this is going to be my embedding just for this simple graph right here. I could also embed, if we want to just look at another state for interest here, what about state D? So state D is 2 away from A, and it's 1 away from B. So this is going to be 2 minus 1 is 1. This distance is 2, so that's going to be 3. So that's going to give it a value of 1.5. Just to make sure. So right, A to I, if this A to D is 2, A to B is 3, which is 5, minus, sorry, this is 1, so that's 4. Okay, I thought I had that wrong. So this is, as I said, this is 2, this is 3 is 5, minus 1 is 4, divided by 2 is 2. And so D will actually be embedded right here. And I guess we'll just do that last point. E right here, and E, so let's take a look at this. E is, A to E is 1, and this is 3 is 4, and this is minus 2, and so E will also be put 1 away. Okay, so this is going to give us an embedding. This is the Euclidean embedding, just like we had with a differential heuristic, and this tells me where my states are on the state space. So 0, 1, 2, 3. And now what we can compute is what is the residual that is left after I do this embedding. B, D, A, E, C. And what I get here, so let's just ask, what is the heuristic between A and E? Heuristic between A and E is 1. So the residual that I get here is 0. The heuristic between E and C is 0. So the residual I get here is 1. The heuristic between E and D is 1, so I get a residual of 0. And between D and B is 1, so I get a residual of 0. Okay, and what that says now is I have my first embedding. And so the first embedding captures something about the state space, and it decides to put C here instead of putting it here. And what it means is now I can build a second embedding of my state space. And the second embedding is actually in a second dimension. We can think of it as a second dimension, but we can also just think of it as a second heuristic. In the online demo I have for this, we actually plot it as a second dimension, so like an X and Y dimension. But practically speaking here, I could just think about a second embedding. And if I want to do a second embedding here, I'm actually just going to choose E and C to be maximally distant from each other. And so E and C are, distance one apart. Everything else is going to sit on E. So we'd have E, A, D, and B here. And we would be able to capture this distance that we didn't capture in our first heuristic. Okay. So, so the idea here is that instead of in a differential heuristic where we sort of stretch our states out as far as we can by placing them according to these distances from the pivot, what we're going to do here is we're going to choose 2 states. And now what we're going to do is we're going to lay out all states relative to these 2 pivots. And really, I mean, this is one possible embedding that you can get, but there are other possible embeddings that you could possibly get here that would also give you, different layouts here. But the key thing here is that once we've done one embedding, we're going to subtract those distances to be able to get a residual in the graph here. And then we're going to build a residual on this graph. And that residual is going to allow us to capture distances that weren't captured in the first heuristic. And most importantly, we can add them together instead of taking the max, which we could do before. And so this allows us to do something, of course, more powerful than we were able to do before. And okay, so this is the high-level picture of what's going on here and how we can use these residuals to get an additive heuristic, because we know this was not captured at all in the original heuristic here. And so let's just look at some pictures here. Again, there's demos of these online. And so what you can do in the online version, which I won't do here, is in the online version you can actually click on this map, and you can click anywhere on the map or on the right or the left. By switching map types, you can regenerate them. And what will happen is that you'll see where the mapping is between a state on the left-hand side and the right-hand side. It's also possible to animate this process. I don't have the animations in this particular slide deck, but I mean, the animation is a little bit fun, but just sort of shows where states match with each other. So we can see here, this is a room map. So it's rooms with openings randomly open between them. And basically the upper left corner to the bottom right-hand corner tends to give us this main axis that goes through the state space. And then we get the secondary axis, which is sort of your other major distances that are going in the other dimension that aren't completely captured here. So if we, for instance, look at just an empty map, what we'd see here is we first capture the entire dimension from a corner to a corner, and then the other dimension is captured. But we get to add these together. So right, any point here. Now here we're in this space, we're adding together the two heuristics. So we are not using Euclidean distance in the two-dimensional space, but we're doing basically adding one heuristic to another heuristic. And if we plot them in 2 dimensions, we get something like this. Okay, so if we take this map, this is a particular interesting map. If you look at this map, if you looked at the differential heuristic demos, you'll have seen this map before. But if you look at this map, what you see here is that actually this map is wound up. It's sort of a one-dimensional map. But at the very end of the map, there's sort of, after you come out of the middle on the top, there's sort of 2 directions you can go there. And so what you see is this map captures these distances across the entire map, plus the 2 major directions that you can choose to go between. If we sort of start at the bottom and go counterclockwise through the map, then when we get into the middle, we can sort of go in 3 different directions. And those give us basically the extra dimensions that we have here. And yeah, so that's showing what a embedding looks like for different problems here. And as I said, the nice thing is that our embeddings allow us to get additive heuristics. So what we've seen here in our section so far on building heuristics is we've seen very parallel look at these heuristics when compared to what we saw in pattern databases. So right, in pattern databases, we started with the initial heuristic, which is built on abstraction. Here we saw our initial heuristic, which is based on true distances. And then we saw that we could compress these heuristics. We could compress our pattern databases. Yes, we can also compress our differential heuristics. And then we saw that we can build additive heuristics using our pattern databases by using a special cost function that doesn't count all the tiles, for instance, in the sliding tile puzzle. And what we can see here is by using a cost function that sort of lays our states out more evenly or uniformly in the state space, we can leave these residuals behind in our graph. And by building new heuristics on these residuals, then we can get additive heuristics as well. So this paints sort of a clear parallel picture between our exponential heuristics and our polynomial heuristics. And we're going to continue. We will look at some other methods of building constraints and search and things like that. But we'll continue to look at these in some of these other techniques in a little bit more detail. But this first piece was really to paint this parallel picture between these ways of creating heuristics in polynomial and exponential state spaces. So we will continue our next lecture looking at, actually we're going to move to jump point search and looking at constraints in search with something like jump point search.